So, welcome. Here we're asked to evaluate this surface integral, where S is the part of a cone, z squared equal to x squared plus y squared between the planes z equal to 1 and z equal to 3. Okay, let's draft a solution for this. The way we go about this, we're given this function here, and we're told that it is between these two planes. That's fine. So we know our integral is going to go from z, our integral in terms of z is equal to 1 to 3. Okay. So that means then this set here is that one. That's fine. So that is fine. So let me just quickly do something here. So we're going to get that minus x squared minus y squared plus z squared is equal to 0. Just took everything to this side. Then when I take the partial of this, partial of x is equal to minus 2x, partial of y, partial derivative, and then partial derivative of x. Take the magnitude of the partial of nabla. It's 4x squared plus 4y squared plus 4z squared all over the root. Here we substitute with f. In this case, it's wise to choose f to the z. So this is 2z, but we know that z is the same as the root of x squared plus y squared. That's fine. We can take out here 4 as a common factor, and that will become 2, and this 2 will cancel out with this 2. So I can do something like this. That's fine. And then here is dx dy. Take this to the right. So I have x squared here. I have x squared here. So what is going to happen is that z squared as well. Z squared is just x squared plus y squared. And then we can multiply with this now. X squared plus, so in a way we can substitute this here. That this will give us 2x squared plus 2y squared. Take out 2 as a common factor, but we're left with 0.2 x squared plus y squared, and then we divide this y over x squared plus y squared obviously let's cancel out and left with 1. Thing about it, here we have now x to the 4 plus x squared y squared dx dy. That's fine. So now let's think about how we're going to take out the limits of integration here. It's between this plane. But we're strategical in a sense that we didn't include z here. So this means then we have to do it in terms of y and x. Okay, so let's substitute the values here and see what we're going to get. For z equal to 1, we're going to get 1 squared, which is 1, equal to x squared plus y squared. This is for z equal to 1. And then for z equal to 3, we're going to get 9 plus x squared, 9 equal to x squared plus y squared. That's fine. So we have radius 3 here, and then we have radius 1 here. So these are circles here. So this is a circle when I believe when z is equal to 1, and that's a circle when z is equal to 2. So in a way we have a representation of where x and y lies. So it's from 1 to 3. From 1 to 3. And then we know. Okay, so let's try and compute this. This would be very easy if we use polar coordinates, meaning that since we know that this is coming here, so we can change this to be 2 root. In polar coordinate x, we know that x is equal to r cos theta, so we're going to have r squared cos squared theta. That's fine. And then we have x squared plus y squared. X squared plus y squared is equal to r squared there. If we're going to write this in polar coordinates, that means then we must have r dr d theta. Okay, that's fine. What are the limits for r? We know that the radius starting from radius 1 to radius 3. So 1 to 3. And our theta is going from 0 to 360, which is 2 pi. 0 to 2 pi. That's fine. So this is the same as 2 and 0 to pi 1 to 3. This is r to the 5, and this is cos squared theta dr d theta. We have that there, so that's fine. So we're going to have 2 from 0 to 2 pi of cos squared theta d theta multiplied by 1 to 3 r to the 5 dr. So I'm going to stop here. This is something that we all can do. So but you saw basically the steps starting from this sort of question and the procedure that I went through, noting that the way you do this could be different This is what we call the magic factor. Could be different, or the methods that you use going to the answer could be different from mine, but basically the method or the concept behind it is the same, I can say. Thank you.